In this lecture, we're going to talk about stellar birth. In the last lecture, we learned about one component of the interstellar medium, the most dense component, the giant molecular clouds. Stars are born when a small part of a giant molecular cloud collapses. Now, one can estimate how long it will take any part of a giant molecular cloud to collapse using the dynamical timescale that we learnt about in our study of the equations of hydrostatic equilibrium. Part of a cloud that has a radius or characteristic size r and a mass m will tend to collapse in a time scale given by this formula here. So it's important to note that a giant molecular cloud will not collapse entirely as a whole. Only a part of it will undergo collapse. Okay, so let's take a section of a giant molecular cloud and ask ourselves, why might it collapse in the first place? Well, to understand that, we have to understand what is keeping it up. Why doesn't it collapse? And that's because there are various forces at work that resist the gravitational collapse of such a cloud. The first one is its internal heat energy. Even at a temperature of 10 degrees Kelvin, the average speed of a hydrogen molecule is still around 800 miles per hour. So the cloud has to be big enough and cool enough to be able to collapse. And there's a characteristic size above which it will collapse. And that depends on the density of the cloud. Typically what happens is the cloud as a whole will steadily grow denser until parts of the cloud exceed the Jeans length, which is derived in the textbook. When any part of the star, say this region here outlined pink, gets dense enough that the region now exceeds its Jeans length, then it will start to collapse. Giant molecular clouds do not collapse as a whole. They will grow denser until different parts of the cloud will start to collapse and form many different collapsing centers. The second thing that resist collapse are magnetic fields that thread their way through the gas. Magnetic fields act as springs. If you try and collapse a magnetic field, it's not going to want to, because the closer magnetic field lines get to each other, the higher the energy density of that magnetic field. So you're going to need to put more and more energy in to bring the magnetic field lines closer and closer together. Just like with a spring, you're going to need to put more and more energy in to compress the spring more and more. The third thing that resists collapse is rotation. The cloud in general will have some angular momentum. It will have some rotation. And it is familiar that if you try and collapse something that is rotating, it'll spin faster, just like an ice skater drawing their arms in and spinning up. But if it's rotating faster, then the so-called centrifugal force is going to be large. It's going to start wanting to throw material outwards again. So that resists collapse. And the final thing is turbulence. Turbulent motion of the gas tends to resist collapse as well. So even if part of a molecular cloud exceeds its Jeans length and wants to start to collapse, there are still these other things that resist. So generally we need something else to trigger the collapse to overcome these other forces. And the triggering mechanism involved is, and the phenomena involved in triggering collapse are shock waves. Just like the shock waves produced in our atmosphere when something exceeds the speed of sound, shock waves are produced in the interstellar medium when outside gas that is traveling faster than the local speed of sound comes into contact with it. And because we're dealing with such low density gas, the speed of sound is very, very small. So it's very easy to get something moving through it faster than the speed of sound. Some other gas cloud, some other region of gas. And that's going to cause shock waves. Shock waves heat the gas, causing it to radiate away energy. The energy associated with rotation or magnetic fields, for example, and that allows the gas to collapse. Here's a little cartoon of the process. A shock wave will pass through a region of a cloud, and that cloud will fragment into parts that will start to collapse. And typically those collapsing parts will also fragment into smaller collapsing pockets of gas. And each of the smallest pockets of gas that is collapsing will eventually become a star. So a particular part of a gas cloud will typically fragment and collapse to produce maybe several dozen stars, or more depending on the size. The shock waves can come from nearby supernova explosions, which throw a lot of gas and dust out at high speeds. It can come from the ignition of hot nearby stars, so if there is some star formation going on nearby, as those stars heat up and fusion kicks in, they're going to throw off a lot of radiation and blow off a lot of dust and gas at higher speeds than the local sound speed. They can also be triggered by different clouds colliding with each other, as I've already mentioned. They can also be caused by the spiral pattern of the galaxy, which, as we will see later on, is actually a density wave propagating through the galaxy. Here's a picture of a reflection nebula containing a small clump of a giant molecular cloud which is undergoing collapse to form new stars. So if we finally got the bit of cloud collapsing to form a star, what happens next? Well, the clumps of compressed gas resulting from the shock wave passing through the giant molecular cloud, well, as the gas molecules fall inwards, their speed increases, and they will collide with other molecules and randomize their speeds. Therefore, they heat up. Gravitational potential energy is being converted into heat energy, just as the virial theorem says it would. As the cloud collapses, its temperature increases, and the central part of the star in particular will become very hot. Thus, the outer parts of the collapsing cloud tend to flatten out into a disk due to their rotation, and it is this disk which could go on to form planets and create a new solar system. This hot glowing ball of gas surrounded by a protoplanetary disk is what we would call a protostar. Here's a very simple anatomy of a protostar. You've got the hot central layer, you've got a region of gas that is free of dust out here that is emitting infrared radiation, and then you have a denser outer envelope, which is where all of the dust is, and that tends to cloak the protostar during its initial stages of evolution. As I mentioned, the cloud flattens out into a disk due to its rotation. The protostar continues contracting and heating up until the center becomes hot enough to start fusing hydrogen into helium, and that is when the star is officially born. At that point, the luminosity increases enormously, and the radiation pressure is enough to drive away the outer envelope of dust and gas that was shielding it from view. And that's when the star announces itself to the galaxy as a whole. Here are regions in the Orion Nebula where stars and solar systems appear to be falling. These are stars that are newly born and are blowing off their outer layers. You can see the hot central layer, which is the star or protostar, and dark region around it is the protoplanetary disk. This year, a very dramatic image was captured by the Atacama Large Millimeter Array. This is an image of the HL Tauri disk, about 40 times the diameter of our solar system. We have the hot central newly born star surrounded by the dust and gas. This is in false color. This is microwave radiation that is being detected. And you can see this definite ring structure. This may be an indication that planets are starting to form. When planets form, they tend to clear out the dust and the gas in their own orbit. So you'll get clear regions where planets are and regions in between the orbits of planets where there's still some dust and gas. As the protostar collapses and heats up, it will increase in its temperature and its luminosity. In the final stages, as fusion starts to ignite, the temperature stops going up quite so dramatically, and the luminosity drops a little as the star is still contracting, and then fusion fully ignites and the star appears at a certain point on the main sequence. Where it appears on the main sequence depends on its initial mass. If you could watch a 9 solar mass star form, it would follow this blue track in the HR diagram and appear high up on the main sequence. A 1 solar mass star like our Sun would follow the blue track here and end up lower down on the main sequence. These blue tracks that protostars follow are called Hayashi tracks. Birth line here marks the point between where we say the star is a protostar and where we say it is a fully fledged star in which nuclear reactions are occurring.